So we most recently finished a chapter entitled Internal Flow, and then we did differential equations, differential analysis of the fluid flow problem. But this chapter is external flow. So we have a body and we have flow over the body. There's a lot of topics, but basically we'll look at drag and lift, and then how to put them in dimensionless form, like drag coefficient, lift coefficient, talk about the friction drag or the skin friction drag, the pressure drag, because you could have a high pressure side on the front of the body, low pressure side on the back of the body, and that can actually be the dominant drag force, the source of the dominant drag force. It's not all just friction, right? Separation is what really leads to large pressure drags. Same type of concept in internal flow. If you don't want a large loss coefficient, try to avoid flow separation. Help the fluid flow streamlines be smooth and bend and go around curves and stuff. Same with external flow. Separation leads to large pressure drags. Streamlining is the object of the process of making the object smooth to help the flow around it. You see that a lot in automobiles over the last 10, 15, 20, 25, 30 years. Pretty obvious. Stokes flow is slow flow. Then you go to high Reynolds number flow. So this is slow, this is fast flow. Flow over flat plates. You just study flat plates because it yields itself to analysis, and then we try to take those results and extrapolate it to things that look like flat plates. But when you first see it, you think, that's a flat plate? Probably not. Boundary layers, they grow, and that's the region in the flow that's affected by the presence of the object, especially the viscosity boundary layer, the boundary layer thickness. Then you have a dimensionless friction coefficient, and a critical Reynolds number, where you have transition from laminar to turbulent, and we have to understand flow over the cylinders, flow over spheres, flow over just a lot of different objects, streamlined as well as non-streamlined objects. Let's just jump into it. Flow fields, you want to do a clicker question right away? Why not? Flow fields over most bodies are complicated and cannot be solved analytically. Hence, designs often are based on correlations based on experimental data. It's true, isn't it? It's true. The flow fields are so complicated that we have to simplify it so much you think that's really even pertinent before we can analytically solve the equations that govern the fluid flow. So when we get the equation that we can analytically solve, we have so simplified the system that it almost doesn't represent the real physical system. We rely a lot on experimental data. We cast that experimental data in dimensionless terms so that we can make the most, extrapolate that data to the most number of cases. The compressible effects are negligible with minimal error when blank. When either the Mach number is 0, Mach number is greater than 0.3, less than 0.3, greater than 10, or less than 0.1. And such flows can be treated as incompressible with little loss of accuracy. A lot of times we have air. Air is compressible. You learned air is compressible, ideal gas equation. But you know, if you have flow over an object and it's not going too fast, you can treat it as incompressible, even air. Well, what is the criteria? Where is the threshold? Everybody in? 5 seconds. All right, do you a world of good if you just kind of peruse the chapter before I get to it. But it's really a Mach number. It's one of these things where the Mach number is less than a third. Professor, why didn't you tell us that before you asked us a question about that? Well, read the book. It's pretty early in the book, okay? And it's one of these things where it'll look like a lot of you did read the book, which is great. So you have a Mach number of 0.2. That still could be pretty fast. And yet air, flow in air, you can treat it as being incompressible, not compressible. Okay, constant density. Now, somebody will always ask about this. They'll say, hey, I've got an air compressor, and that air compressor takes it and squeezes it so the pressure ratio is maybe 10 to 1 or something. But it's not going fast through that air compressor. Can I treat the air as incompressible in my air compressor because the speed is never above 0.2 Mach inside the air compressor? Well, that's a whole different thing. I've got an air compressor changing the pressure by like 10 to 1 or something, 9 to 1. No, it's compressible, okay? It's like this Mach number is for, this criteria less than 0.3 is for like a constant pressure flow over an object where it's coming to rest in some places and then speeding up in some places. So, the velocity of the fluid approaching a body is called the blank and is denoted V. Sometimes you'll see cap V with something like that, or maybe U with something like that, or cap U with something like that. So what is this called? This velocity of the fluid that's approaching the body and then going to go flow externally over that body. Is it the body velocity, ground velocity, free stream velocity, two-dimensional velocity, or skin velocity? Look at that. We have great participation today. 100% said free stream. Meaning what? It's not a feeling the effect of the object yet when it comes around the object. So we have a free stream flow, we have an object, and there will be some region in which the object's presence is strongly felt. But even far away, it doesn't even feel the effect of the object. All right, it's free stream. Clarification or classification of bodies. A body is said to be blank if a conscious effort has been made to align its shape with the anticipated streamlines in the flow. Well, what type of body is that where they basically are designing it such that, like the shape of an automobile? Aerodynamic body? Sure. But is it a bluff body or a streamlined body? It's a streamlined body. So it's easier to force a blank body through a fluid. A bluff body or a streamlined body? Which one is easier to force it through the fluid? Streamlined body. Streamlined body is easier. So that's why that people streamline different things. Okay. The force a flowing fluid exerts on a body in the flow direction is called, so here's my body. Looks like a bluff body, doesn't it? Not very streamlined at all. And then here's the flow field. And there's a force that the fluid exerts in the direction, in the flow direction. And that's called the push force or the push, fall, the drag, or the mosh. Which one is that? Should we do a clicker? Why not? Easy day today. Lots of clicker questions. A lot of times we show the flow direction as being in the X direction. True? True. All right. Well, let's see what we got here. Are we 100%? Oh, no. Well, it's the drag. It's the drag force. That's the term, drag. If you flipped open this chapter and just looked at the chapter titles or the main headers, you'd see drag and lift, drag and lift, drag and lift. What exactly is drag? It's the net force that the flow exerts on the body in the direction of, not the direction of the orientation of the body, but in the direction of the flow direction. The flow direction. Somebody takes that body and they say, oh, I want to take that body and kind of move it like this. Does that mean the drag force is in this new direction aligned with the body? Nope. It's always aligned with the flow direction. So we have drag force. There's two types of things that contribute to the drag force. One is probably the one that you understand the best, coming from this equation. What's that equation called?
And what do we call the dynamic viscosity?
That's a dynamic viscosity. is basically our, well, some people will call it Newton's law of viscosity, but too many things are called after Newton. He did too much work. We have to stop honoring him so much. So it's the law of viscosity. And so, yeah, this is that property of the fluid, absolute viscosity. This is the change in the speed as you're moving away from the body in the y direction. If you want to evaluate this at W, what do you mean by at W? What's W mean? Tau. That's a shear stress, a viscous shear stress. At the wall. What do you mean the wall? At the interface between the fluid and the solid. True? And so that would give us the skin friction drag. What's the pressure drag? Well, I have an object like this, an object, and the flow is going this way. What do you think is going to be, why do they put these plus signs on this side and minus signs on this side? What does the plus and the minus sign indicate? Higher pressure. Pressure is a force per unit area. Just like the force per unit area, but this skin friction was not a force normal, it was a force tangential or shearing force. Okay? This pressure is normal. And so it would be a high and a low pressure on both sides. Hence, that would give you a net drag force on the object. So we have the pressure drag and the friction drag. They both contribute to the drag force. Sometimes, for one object, let's do this one. This is just easy. If I have a very thin little object like this, okay, and the flow is going this way, which one of these two dominate the total drag force? The skin friction drag or the pressure drag? Skin friction. If I have an object that's shaped like this in the direction of the flow, which one do you think dominates? The pressure drag. The pressure drag. And then you used to have different objects and there's a balance between them. All right. Separation is what you want to eliminate. Why do you want to eliminate? Because it creates a lot of low pressure on the backside of the object. So if I have an object and it looks like this, that's kind of nice. Front has been streamlined a little bit, but what's going to happen right in here is the fluid is going to be able to flow around the front of the object fairly well. The streamlines in the fluid will be along the surface of that front of the object. But will they flow like this on the back side of the object? No. You're going to get a big separation region where it's going to kind of go around like that, go around like that, and then you'll have this big region of recirculating low pressure region. So anytime you can try and streamline, notice on some of the semis now they'll put little fairings in the back of the trucks. Did you see that? Yeah, I think there's a little crank to deploy them. What are they trying to do? Help that flow in the back side, reduce the pressure drag. Also, if you look at semis in the trailer section now, about a couple years ago, they started putting little skirts on them. That's exactly the same thing, little skirts. So streamline, that's design intent. You try and make the contour and the flow lines, have smooth bends to them and not have separation. What's the drag coefficient? Well, C sub D, what do you think? What do you think it's going to be defined as? The net drag force proportional to, we're divided by dynamic pressure. We like that dynamic pressure. Well, what's this V here? Sometimes you write it cap V, sometimes V infinity, sometimes U infinity, sometimes cap U infinity. What's that V again? Free stream velocity. That's the fluid approach velocity. When it starts to go around here, maybe it speeds up. Maybe it's a little faster speed of the air coming around the nose of that object. True? And maybe in the wake region, it's a lot slower. But we're talking about the free stream approach velocity. Okay, what's rho? That's an easy question. What's rho? Density of the fluid that's flowing over. A lot of times it's air. A lot of times air is not considered compressible. You're not taking that semi and going Mach 5 down the highway. I know a lot of truckers like to try, but they're not doing Mach 0.5 or anything like that down the highway. So the air is not changing density that much. So we treat it as incompressible. And then what do we have right here? Well, look at the SI units of this one. That's force, like newtons. What's the SI units on this one? That's a pressure, newtons per meter squared. What do you think I need? I need an area. Now, what area makes sense?
Frontal area?
The frontal area. AF, frontal area. So if I go far up here and I stand right here and I look at that in the direction that the flow is going at that object, I get a silhouette, and that's my area for the drag. Make sense? All right, so that's the frontal area, the silhouette area. Give an example of an axisymmetric flow over a body. I have a body. What's it mean to be axisymmetric? Well, introduce an axis, and then say that if I took some profile of it and just revolved it 360 around that axis, that's what the object would look like. True? So take something, maybe if I did something like this, I don't know, what would this look like? This is a crazy, that area, and then I revolved it around, that would not be a very, well, it would be an axisymmetric body, but it sure wouldn't be very streamlined, would it? So what would be an example of an axisymmetric flow over a body? Well, I need a bullet. That's it. And so then you would revolve that around and you get the shape of a bullet. Okay. And give an example of flow over what they call a bluff body. Well, that's not streamlined. What's a bluff body?
Kind of what you just drew.
Yeah. This would be a bluff body. So if I have flow coming this way, would this be a bluff body, flow going that way? Would this be flow going this way, a bluff body? Yeah, it would. Now, this one, you know, I know that it's tough here, but if you turn it, the object this way, let's say this is a cup, like half of a what do you call that? Shell of a sphere, and you turn it one way and you turn it the other way, it'll have dramatic different effects on the drag on that object in the same flow field. All right, but neither of these I would say are streamlined. All right, but they're pretty bluff. The only time average force exerted by the fluid on an axisymmetric body aligned with the flow is the drag force. A, true, B, false. What do you think? The only time averaged force exerted by the fluid on an axisymmetric body aligned with the flow is the drag force. It's true. That's true. I'm sorry I didn't have a time for clickers. I'll have more questions. How about this one? The net force a flowing fluid exerts on a body in the direction blank to the flow direction is called lift. Here's the flow direction right here. I put some body in there, right? And then we've been talking about the force that's aligned with the flow direction, and we've been talking about the drag force. Now all of a sudden you change this four-letter word from D-R-A-G to L-I-F-T, lift. Well, you threw us a curveball. I didn't look at the book before I came to class, but I'm just going to guess that the lift is going to be 90 degrees related to the drag. So if that's true, then the lift force is opposite the flow direction? Like the lift is going that way? Nah. Normal? Yeah, that sounds abnormal. Aligned? That's kind of aligned. parallel. That's kind of parallel. Which is our best answer? Normal, meaning normal is perpendicular. It would probably be easier if somebody said perpendicular, true? But they use the term normal, so we should use the term normal. Why do we not have 100% on that? That's okay. Here's a problem. An object is oriented at an angle of 20 degrees. So there's an axis to the object, and the axis of the object's oriented 20 degrees to the flow direction. That's why they're showing this 20 degrees right there. The net pressure and viscous shear force, so two contributions, pressure force, shear forces, acting on the object is a force that is 750 newtons at an angle of 25 degrees with the flow direction as shown. So there's a 25 degrees. Calculate the drag force on this object. Calculate the lift force on this object. What would be the answer for part A? The force drag would be F resultant times cosine 25 times cosine of 20? No, come on. Does the 20 degrees come into play or not? 20 degrees does not come into play. Anything using sine or cosine of 20 degrees is wrong. So how about for part B, the lift would be that F of R, that component of F of R, which is perpendicular or normal to the flow direction. So we have now introduced that lift force. Again, the lift force is normal to the flow direction. Okay. Now, we had a drag coefficient. Now we have a lift coefficient, C sub L. It'll be the magnitude of the lift force, SI unit, something like Newton, kilonewton. What do you think I normalize it by? What do you think we divide by? Dynamic pressure, 1/2 rho V squared. That V is called the free stream, sometimes V infinity, sometimes U infinity, sometimes cap U infinity, whatever. But that's what that fluid approach speed is, that free stream speed. And I need something else. What do I need right here? An area. But should I stand in front and look at the silhouette area in the direction of flow, or should I change my perspective for lift? So if I have my object, in a lot of objects, let's say a vehicle driving down the road, we don't want to generate lift. We just, if you want to do anything, sometimes in race cars, they generate down lift to push down on the back tires so that you don't ever start to leave the track and you have good traction. That's what they do. But if you think about an object that wants lift, you're thinking about an aircraft. And aircraft are very streamlined, and they have things that are wings, true? So should we look from this perspective out here that way to look for an area? Or should we get way up here and look that way for the area? From the top. We should look from the top. And so now that area, there's some different names for it, but plan form area. Did I make up that word? No, I did not make up that word. Plan form area. So it's that from a distance looking down on the wing, it's that silhouette area. Okay? So it looks like the drag coefficient and the lift coefficient have a lot in common. It's just the perspective of the areas. The blank force is the force a flowing fluid exerts on a body in the flow direction. I will go ahead and ask that clicker question. Drag, lift, draft, draft, lift, drag, vertical, or wake. And I'm glad to see 100% correct. True? The blank force is the force the flowing fluid exerts on a body perpendicular to the normal flow direction, or normal to the flow direction. What would that be without the clicker? Be lift, true? Lift. Drag is caused by two different effects. Clicker, here we go. Drag is caused by two different effects. Pressure, gravity, friction, geometry, pressure, friction, friction, gravity, pressure, geometry. So, what is it? Friction is one, and pressure is the other. Isn't it? Isn't it pressure and friction? Yeah. So the skin friction component and then the pressure component for the drag. Terminal velocity. So I take this object and I let it fall in a fluid. And after a while, after it falls for a distance or a long time, either way you think about it, it reaches a velocity where it's the terminal velocity. It's a free falling velocity in the stagnant fluid. How would I calculate that terminal velocity? Well, I do a force balance on my object. True? So if it's falling, if this is the direction of the fall, this is V, the terminal velocity. Let's just leave it without a subscript, V. Then what forces do I have on this object? Do I have this force, which is F of D, the drag force? Yeah. Do I have the weight of the object? Hey, if it doesn't weigh anything, it's not going to fall, right? So it's got to weigh. And then if you really wanted to be careful about it, you could fall in a liquid or you could fall in air. So if you do fall in a liquid versus a fall in air, there's another force on it. What force would it be? Buoyancy. The buoyancy. And so maybe you put it like this, the F buoyancy. Now, the drag force we can unravel. We'll say, hey, somehow I'm able to get the C sub D. I forgot what C sub D is. The name of C sub D is drag coefficient. Multiply that times some A, silhouette area, the projected area in the direction that it's falling through the fluid, times some 1/2 rho V squared. What is that V this time? Well, that's not the free stream velocity, it's the terminal velocity. That's the speed of the object through the fluid. Well, if you change your reference state and you say my reference, little reference for looking at velocity is falling with the object, then the fluid is approaching it at the free stream. So yeah, it could be also considered a free stream velocity. What about the buoyancy force, F of B? Let's put it over here. F of buoyancy. What is my equation for the buoyancy force? I forgot. Whose principal gave us the equation for the buoyancy force? The name of the individual? I heard it. Archimedes. And so what is the whole concept of that buoyancy force? The buoyancy force equals the, you're supposed to rattle it off. We passed that part of the class already. The buoyancy force is equal to the weight of the fluid displaced. The weight of the fluid displaced. How can I write an equation for the weight of the fluid displaced? It would be equal to m times g. What is m? The mass of the fluid that was displaced. Well, the mass of the fluid displaced would be the density of the fluid times the volume that's displaced. Let's distinguish that V from the other V by saying, hey, this is the volume V. True? So what is that rho of F? Or is that rho of the solid that maybe is the... No, it's the density of the fluid that's being displaced by the solid. So it's not rho S. A lot of people will say, yeah, they'll put rhos of S. Let's say it's a copper sphere or something in water. They'll put the density of copper there. No, it's not that. It's the density of the water. All right. Does this look okay? Yes or no? Yes. And then what about the weight? Give me an equation for the white. It's equal to the mass of the solid. I should have put a mass of the fluid right there, times G. Isn't it the mass of the solid times G? I'm thinking a solid that's being dropped through the fluid is equal to the density of the solid, the volume, G. Are these volumes the same? They are the same. That's right. So now you have a very simple equation you can solve for the terminal velocity. So let's just go very slowly through it. Drag force, maybe I put a lowercase d before, I'll stay with the lowercase d. And the buoyancy force equal to the weight. The drag force is the drag coefficient. That projected area, the frontal area, 1/2 rho free terminal velocity squared, plus the density of the fluid, the volume of the object, G, equal to the density of the solid, volume of the object, G. And so you could solve for the unknown terminal velocity, V, and calculate it for an object. Okay, what happens if the drag coefficient goes up for the same size, same other things, same area, silhouette, same volume? What happens to the terminal velocity? Go up or down? If the drag coefficient goes up, it'll go down. It'll go down, right? It'll go down. True? For the same projected area, for the same volume. Okay. There's other things you could do. You could say, how does the density of the solid, let's say instead of a copper sphere I drop a lead sphere. Okay? Does it change the C sub D? No, that's on the shape. It's the sphere shape. Does it change? No, the same area or diameter of the sphere. It doesn't change the density of fluid, but it changes the density of solid. Which one's going to drop faster? The copper sphere or the lead sphere? Lead is heavier. Lead, because it's, yeah, I'm just changing, I'm just playing a game and saying, now let everything else, and then you increase the density of the sphere, it'll lead to a higher drop speed or terminal speed. All right, let's say I change the density of the fluid. I have water or I have air. Which ones have its higher density, water or air? Water has a greater density. So which one is going to have a higher terminal velocity? Air. You can use your intuition on that and then back it up and you could calculate. All right. Stokes flow. You can have very low Reynolds number flow. That's what that means. And when you have very low Reynolds number flow, you have that the drag coefficient is a constant divided by the Reynolds number. What happens is let's say I have my object right here and I'm having flow over that object. Well, in Stokes flow, the flow isn't going very fast. It's low Reynolds number. It's slow flow. True? So when it's slow flow, it's easier to navigate the backside. So less prone to separation. So it's going to navigate the backside. Okay. So what will happen is as the flow, let's track a chunk of fluid and you just tell me a little bit about the fluid. Here it is, it's moving here, moving here, moving here. Is it speeding up as it's moving from A to B to C to D? Is it speeding up? No. But let's say it goes from here, A to B to C to D. What happens in that sequence, A, B, C, D? What's happening to the fluid? Is it speeding up, slowing down, or staying the same speed? It's coming to the tip of the object. Slowing down. It's slowing down. But now it's going around the object, A, B, C, D. Speeding up. So maybe we should write these down. In this section right here, the fluid is slowing down. Why? Because it's seeing the front of that object. If it was a pedostatic tube, what would theoretically that chunk of fluid that is just perfectly aligned with the very tip of the pedostatic tube, what speed would it slow down to? Zero. It would slow all the way down to zero. But the fluid that is just a little above or below that, it's not going to slow down to zero, but it's still going to slow down, and then it's going to navigate around. But once it starts to navigate around, what's the little chunk of fluid doing? Speed up. Then, what about over here on the back side? What's the little chunk of fluid from point A, B, C, D? What's the little chunk of fluid doing? Slow down. Where is the fluid chunk going the fastest? The fastest. Where is it going the fastest? Probably right at the top. It's going the fastest. True? Okay. And then where is it going the slowest? The slowest. The tips. The front tip. And what about the back tip? It's the same. It's the slowest. But now let's do this. 1, 2, 3, 4, A, B, C, D. What's happening there? It's not out here, A, B, C, D. Way out here is when it's A, B, C, D. It's like no more changing of speed. It's no change. No change in speed. It's far enough away from the object. Just like right over here. No change in the speed. But what about here? This one right there. What's happening to it? Speeding up. It's speeding up. It's like you could take this thing, you could cut it right there and flip it. Let me try and draw it with a different color. Cut it right there and flip it. It'd be symmetric. It'd be symmetric. I know the object has to be symmetric. I tried to draw a symmetric object, but the flow field would be symmetric as well. So in that case, the contribution of having high pressure on the front and low pressure on the back, the pressure drag, guess what? It is low, negligible, theoretically goes to zero. But what about the viscous drag? It dominates. It dominates the total drag. The friction drag dominates. And so in those cases, you get that the equation, I didn't prove it, is the drag coefficient comes out as a constant over the Reynolds number. Have we ever seen anything in fluid mechanics where you see something like some drag is a constant over the Reynolds number?
Friction coefficient.
Friction coefficient from internal flow. Now, let's go ahead and review internal flow. Wasn't that for a pipe? And what we had was we had some friction factor is 64 over the Reynolds number. If we had internal flow where it wasn't quite a circular cylinder, it would be a constant divided by the Reynolds number. And they gave you different constants for if it was this shape or that shape or that shape, you know, some, or even this shape of a circular pipe or circular duct. Not circular, but a duct, okay, or some cross section gave you a different constant, but it was always some constant divided by the Reynolds number. That's the friction factor. What contributes to that delta P, that pressure drop or pressure loss from over a distance? What contributes to it? It's due to the viscous shear stress at the wall. And so it's a very similar thing here for low flow external. It's all shear stress at the surface of the boundary. These questions help reinforce the concepts. So the drag coefficient is defined in terms of the frontal area for bluff bodies. It's true. The drag coefficient is defined in terms of the planform area, not the frontal, for slim bodies such as airfoils. As soon as you switch to airfoils, the drag coefficient, that area, doesn't make sense anymore that it's the frontal area anymore. So when you go to a body that's an airfoil, a slim body, whose purpose is to generate lift and minimize drag, even the drag coefficient now uses the other area. Okay? So if the purpose is to generate lift, then use for the lift coefficient and the drag coefficient, not the frontal area, but the planform area. The planform area of an object is the outline or silhouette for an object viewed from above. The chord of the wing is line connecting the nose and the trailing edge, length of the top surface, circumferential length, perpendicular length, or frontal length. Sorry I started a clicker question. Better read quick. And what I'll do to help you there's everybody's responses. I go with the flow. But you only got a couple seconds.
Thank you, sir.
All right, there you go. Did it help?
Yeah.
I think it's 100% correct. Congratulations. So when you have that object, and you have the nose, and then you have the trailing edge, and it's that straight line length, and maybe the shape underneath is a little different than the shape on the top. And that gives you the wing. That gives you the wing. All right. Which statement is true? The friction drag is a strong function of viscosity and increases with increasing viscosity. Well, what you want to do is break it in part. And so if the statement's true, the first half as well as the second half is true. So just look at the first half, part A, or the first half. Which one? The drag coefficient, the friction drag is a strong function of viscosity or a weak function of viscosity. Which one is true? It's a strong, so these are gone. You don't have to consider them anymore. It's just between A and C. Now look at the second part. Get rid of this and get rid of that. And increases with increasing viscosity. Or does it decrease with increasing viscosity? What does the friction drag do? It increases with viscosity. So the right answer is A, isn't it? Okay. The friction drag is 0 for a flat plate normal to the flow. So this is out of the textbook. They have an illustration. They take a plate right here and they put it in the flow field. The flow is coming this way. So guess what? The flat plate's not parallel, but it's perpendicular or normal to the flow. So guess what is this huge? I mean, that's where it separates, and you have a huge wake region behind the plate. Okay. The friction drag is 0 for a flat plate normal to the flow. True or false? We'll take a clicker question on that. True or false? The friction drag is 0. So as a little review, you have the total drag force is made up of two components that contribute to the drag. One is the friction. One is the pressure. One you can think of, I have high pressure, high pressure, high pressure, high pressure, low pressure, low pressure, low pressure, low pressure. That's like the pressure drag. Sometimes they call that the form, F-O-R-M, form drag, because it's high, low pressure on another. The friction drag, or the skin friction drag, is associated with having the viscosity and the rate of change of U with respect to Y. Well, for this problem, for a flat plate, normal to the flow, which one dominates? The pressure. It's high pressure, 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 low, 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 low in the wake. And even if we did have some friction, the flow along the line would be going this way, which would contribute to kind of pull the top up and push the bottom down, not really in the direction of the flow. So it's true. This is true. The friction drag is 0. That's true. Why would you say it's not true? Actually, you can find that statement somewhere in the textbook. I didn't write down the page, but it's in the textbook. What page? 614. Look at page 614. Low Reynolds number flow, C sub D is equal to constant over the Reynolds number. Now, remember what the drag coefficient was defined as. Can you remember? It's a drag force divided by some projected frontal area times 1/2 rho v squared. True? How would we use this? Well, we would unravel and say the drag force, when I want to use it, is equal to the drag coefficient, that area times 1/2 rho v squared. If I'm moving faster in the fluid, I get a larger drag force. True? So if I say that the drag coefficient is equal to a constant divided by the Reynolds number, rho v, some length over mu. Did I do that right for replacing C sub D? Then I have the projected frontal area 1/2 rho v squared. Are these v's the same? This v, can I cancel one of those v's? So what we find is that the drag force is proportional to the speed when you have low Reynolds number flow. When you have intermediate Reynolds number flow, well, it's a true function of Reynolds number. But just like in some other cases, you get to what they call Reynolds number independent. When you get really high Reynolds number flow, guess what the drag coefficient does? It goes to a constant. It goes to a constant. Think about in the Moody diagram, was there any region where it was Reynolds number independent? There was. It's like where the friction factor went flat as a function of Reynolds number. What did they call that in internal flow and pipe flow in the Moody diagram? They called it the what region? Completely turbulent, fully turbulent, some terms like that, different authors, different names. But the friction factor was no longer a function of the Reynolds number. You have the same behavior here for external flow. You can get that the drag coefficient becomes a constant, and this is very common in external flow that you get this case here. This is less common. This is very common or more common. All right, so if that's true, then guess what the drag force is proportional to? It's proportional to the velocity squared. So you could plot something like this. Drag force as a function of velocity. If I plot something where it's proportional to v, it looks like that. Plot something proportional to v squared. And so you're out here and you increment to this much. Well, yeah, you have some increase in the drag. Here you have some real increase in the drag. This is true for a lot of things. Let's say the drag force on an automobile. It's going 30 miles an hour, and then you decide, oh, I know the speed limit's 30, but I'm going to go 35. I'm in a hurry. True? Does it increase the drag coefficient on your automobile when you increase the speed from 30 to 35? Yes, it does. You're doing 80, and you say, well, I'm West Texas, 80 is the speed limit, but I really want to go faster, and I'm now going to boost it up to 85. Only a 5 mile an hour increase. But the drag coefficient went up a lot more, going from 80 to 85 than from 30 to 35. Because it's proportional to v squared. So this is a great table. I wish I had more time to just walk through every item in this table. I encourage you to walk through every item in this table. So here are some representative drag coefficients, C sub D's, for various three-dimensional bodies based on the frontal area for a Reynolds number greater than 10 to the fourth unless otherwise stated. Why do they say that? Because they're just going to give you one value of C sub D. One value of C sub D. One value of C sub D. What are they really telling you when they say it's one value of C sub D? Well, it's for fast flow. It's for Reynolds number independent flow. And so in these cases, the drag forces are always proportional to the velocity squared. And that drag coefficient comes in the equation. So let's take a look. Here's a sphere. Now make sure that if you're turbulent, you're above 2 times 10 to the 6, the drag coefficient's 0.2. Okay? Look at a different figure if you want to compare smooth and rough spheres. And you want to get it as a function of Reynolds number. We have that figure. We'll show it to you. But here's a cube. The drag coefficient's about 1. Here's a disk, 1.1. Here's a cone, 0.5. You know, that cone has a lower drag coefficient, doesn't it? Even though it may have the same diameter. But the flow is, the front area is going to help it split it. So that's why the drag coefficient drops. Here's an interesting one right down here. A hemisphere, true? So this would be a solid, and in that solid, either the front helps split it, drag coefficient 0.4, or it's like a flat disc with a little on the back side, 1.2. Take a look also at, I truncated it, sorry, the parachute. The parachute lets air go inside and then kind of pushes it around. Maybe that doesn't show up so well, the color. And when it comes around, then so this really a large drag on a parachute. That's what the purpose of the parachute. The purpose of the parachute is put you a large drag coefficient out there, a large drag force, so you don't fall as fast. True? Yeah. Okay. There is a lot in here. If the biker's sitting upright and he has a certain area and a drag coefficient versus he's racing, he has a streamlined, a smaller projected area that helps reduce the drag, make a smaller area, as well as the drag coefficient because he's more streamlining, kind of shooting things over. Sometimes they wear special helmets and do other things to help streamline. Here is an automobile. You have the area, the frontal area, the minivan, not as streamlined as a sports car. But you know, you can work a lot, and it may be, maybe you had a vehicle that was at 0.5 to get it to 0.4. A little bit of streamlining will do it. 0.4 to 0.3, a lot of work, a lot more work. To drop it from 0.3 to 0.2, you're going to do a lot of work. And I think there's a lot at 0.2 and 0.25 in that vicinity, and it's too much work to drop it lower. You need a mirror for safety. Put those mirrors out there, right? If you got rid of the mirrors, it'd be streamlined better instead of those big Dumbo mirrors sitting out on the side. But you'd have more wrecks. So let's leave the mirrors. True? And then there's something about fitting stuff in the trunk. People like to buy stuff. They look to open up the trunk at the car lot, and they look inside and say, my stuff can fit in this. That's great. I'll buy it. You get an itty-bitty trunk. They open it up. Forget it. Let me look at another model. Right? Could be really streamlined, but it doesn't fit the needs of the customer. We have a 1.2 centimeter diameter ball made of cork, so you get the density of the cork. It's free falling in air. There's a density of the air, viscosity of the air. Calculate the terminal velocity of the ball. I think we did that. We could do that, true? What are the three forces you need to consider? Weight, buoyancy, drag. Because it's a ball, you're going to need to get the drag coefficient. How sophisticated do you want to be? Is that drag coefficient going to be a constant? If it's high Reynolds number, typically that's what you do. Or is it going to be a function of the Reynolds number? Yeah. Or could it even be a constant over the Reynolds? I doubt it, because that would be like Stokes flow. That would be really slow flow. That model probably is not applicable. It's probably some function of the Reynolds number to get the drag coefficient. And then you would, once you solve for the terminal velocity, you could go back and interrogate what exactly is that aerodynamic drag force at the terminal velocity. I think we're equipped with all that. It's really, how am I going to get that drag coefficient? Oops, I think I have it on next slide. No, I don't. So, let's answer these questions. At high Reynolds number flow over common geometries, the drag coefficient is a constant. True or false? I will just let you answer it out loud. It's true. That's true. How about this one? We'll answer this clicker. For high Reynolds number flow over common geometries, the drag coefficient is proportional to the Reynolds number. The drag coefficient's inversely proportional, whatever. The drag coefficients, blah, 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 blah. All right, well, I guess it's this problem. What's the difference in the first problem? High Reynolds number, common geometries. We already agreed the drag coefficient is a constant. The drag coefficient is a constant that does not depend on the Reynolds number. This is terrible. It's either too much reading, too many words. Is that it? Is that what it was? Too many words that you couldn't read it all? Because when you get a distribution like this, the distribution like that, you think, well, there's some guessing going on. I don't have time to read it. I think it's a D. Push it and push forward. All right. For high Reynolds number flow over common geometries, the drag force is independent of the flow velocity, drag force inversely proportional to. So this is the drag force is equal to a constant. That's another way of saying A. Or the drag force is proportional to 1 over the velocity. That's B. The drag force is proportional to the velocity. The drag force is proportional to the velocity squared, or the drag force is proportional to the velocity cubed. Let's do the clicker on this one. Maybe it'll help. And then I'm going to stop the clickers, right? We had enough clicker today, huh? Aren't you tired of clickers? They're okay? Not bad? Really? 13, 12. Okay. Well, when you had high Reynolds number, the drag coefficient's constant. And so what happened is the drag is proportional to the velocity pressure. And so D is it. Woo, good job. All right. Now there's one other thing is, what is the power required to keep a system pushing through the fluid, right? If I have an automobile and the engine dies, will I still go 60 miles an hour down the road till I hit Houston? No. What's going to happen? The friction drag, all that. But if you just think aerodynamic drag, forget about the bearings and the rolling resistance. You have to overcome that to drive at constant speed. True. So what is the power that the engine has to provide to keep the vehicle moving through the fluid at constant speed? Isn't that the product of the drag force times the speed? Isn't that my basic dynamics mechanical power equation? So if this is in a region where the drag coefficient's constant, a lot of cars driving down the road 60 miles an hour, that's what it is. It's a constant drag coefficient. Then this is proportional to V squared. You multiply by V. And so the power is proportional to V cubed. So my car may be able to do 60 miles an hour. But when I try to do 80, the engine just try to do 90, forget it. But then some other people have 400 horsepower packed inside that, and they can do 100, and they want to do 120, no sweat, and then they can do a little bit more. But it really takes a lot of power from your engine to go fast. And the difference between going 100 mile an hour and 110, don't do it. Don't do it. Don't do it. Don't do it. It's too dangerous. But it really goes up. And to think about, what are the NASCAR guys running at, or the Formula F, whatever, what are they running at? That is a lot. That is a lot of power to keep a car going at some of those speeds. Somebody said 200 miles an hour. That's incredible. Aerodynamic drag coefficient on automobiles is negligible at low speeds. Let's say it's less than 30 miles per hour. If you're driving at 15, 20 miles per hour, the aerodynamic drag is usually negligible. True or false? True. It's true. It really kicks in because it goes as v squared. So at low speeds, negligible. For a car moving on a flat road at a high speed, 60 miles an hour, the power developed by the engine to overcome the aerodynamic drag is independent of the vehicle's speed, inversely proportional, proportional to v squared, v cubed. Which one is it? V cubed. That really goes up. That really goes up as the speed of the vehicle goes up. To improve the fuel economy on a low drag automobile, that means you bought one of those high efficiency, they made it really tight, streamlined, front and the back, and they got that drag coefficient down. They got it down to, I don't know, 0.25, 0.24. It is better to turn the air conditioner off and roll down the windows and drive that way. What do you think? That's false. Because what did you just do? You just destroyed that drag coefficient. And it's now a very high drag coefficient because the side windows are down. Or maybe you have a little vent glass in the front. You open it up and it's a wind scoop. Wind scoop, that's my air conditioning. Open it up and then blow the air in. Okay, so this is not true. It's false. A lot of times, if you really want to improve it, turn the air conditioner off, that's true, and sweat. Hey, that's not the purpose of the air conditioner. To calculate the drag force on a complex body, let's say I have a wing, a fuselage, a wing, a tail. There's a complex body. Think about the flow over the wing, over the fuselage, over the back, over the tail, and then sum them up. What do you think? Good idea or bad idea to get the total drag? Good idea. What do you call that idea? Principle of superposition, supposition, dereliction, determination principle, or hydrophonic principle? Superposition, right? No more clickers today. We're tired of clickers. Or I'm going to have to stop in a couple minutes. Flow over flat plates. All right. When you have a knife edge sharp plate right here, and you're only looking at the top half of the flow over the top half of that sharp plate, this is the tip. You have the free stream velocity of the fluid approaching it. If a little chunk of fluid is out here, it doesn't even know that that plate exists until maybe way, not even on this. But if the fluid chunk here, it doesn't know it exists, but all of a sudden, oops, I now have felt the presence of that plate. But if it's right here, oh, I feel the presence of the plate and am affected by it. So what we have is a region, it's called the boundary layer region over that flat plate where the presence of the flat plate is felt. So what does it do to the fluid chunk that comes right there and tries to skim along the top of that plate? Well, it slows it down. So because that plate is stationary, it has zero speed, there's a no slip boundary condition. So the fluid attached to it or right adjacent to it, that millimeter or that not even a millimeter, fractions of a millimeter, it's not flowing. The fluid is brought to rest right there. And then you have this profile where the velocity goes toward free stream, and now it's back to free stream out far enough away. So you have a region that develops, and they call that the boundary layer region. At first it's laminar, and then after a while, if the plate's long enough, then the presence of the competition between inertial forces and viscous forces in the flow field could make it transition to become turbulent boundary layer. When it does transition to turbulent, it grows at a different rate than when it was growing when it was laminar. And you have more, what are they showing with these arrows like this? Instead of the arrows always being nearly linear, parallel, you have them going in all sorts of mixing. So yeah, it's like mixing in the turbulent region. Mixing is enhanced with turbulence. It's like chaos, but it's not really chaos. It's you can think of it as chaos, but it's really just fluctuating flow. That's turbulent. The time average speed at a point is still like that, but you have to average over a time interval to get the average speed. So this is a turbulent boundary layer. Now, very close to the plate, it's still viscous sublayer. And then they have some other layers where you transition from the viscous sublayer out to the fully turbulent boundary layer. All right. So what is this boundary layer thickness? Distance here. You can define it for in the laminar region, transition region, turbulent region. It's where the velocity at that distance going out is 99% of the free stream velocity. So if it's slowed down to 98, 95, 90%, 70% of the free stream velocity, you're in the boundary layer. But if it's 99% of the free stream, guess what? Basically, you're out beyond the boundary layer. That's the definition of the boundary layer. Why didn't they define it as 98%? I don't know. Why not 99.9%? I don't know. The consensus is it's 99%. I'm sure the first people that studied it said we really can't, our instruments can't really measure anything less than 1%. So there you go. Okay? All right. So what is the criteria for the boundary layer thickness? We just talked about it. It's where the velocity goes from 0 up to 99%, not 98, 99.7. It's 99%. And thankfully, when you pick up different fluid mechanics books throughout the literature, nobody's sat there and said, I really think it needs to be 98% or 98.5%. It's just 99%, okay? That's nice. Nice to have consensus. Now, inside, if you put a little smiley face, and then you see as that smiley face flows down in that region inside the boundary layer, that smiley face is going to end up rotating. And that flow inside the boundary layer will be called rotational. True. But if you put the smiley face outside the boundary layer and you just let it float, it is not rotational outside the boundary layer. It is irrotational, not rotational. Okay? So to say the flow outside the boundary layer region is rotational is false. Inside, it is rotational. Yes, true. Make sense? Just the quick one. First time people look at that plate, they think, oh, that's just the top surface. But what would be the difference if I had flow approaching, case A, a very thin knife-edged flat plate versus a thick boxed edge, that's my flat plate for case B. What do you think the flow at the top half? I'm interested in studying the flow up here in the top of the plate, right? Do you think either one of these is going to have different flow conditions or configuration? Yeah, of course. Because this is going to come to rest, and then it's going to try and go, and then it's going to separate. And so when we study these flows over flat plates, it is a knife-edged flat plate so that I don't have a flow separation right away at that tip due to this flow trying to get around and around on the sides. Okay, that's a big deal because we'll apply the equations that we generate, analytic solutions from this simple solution to the top of a semi going down the highway. There's a lot of trying to divert the flow to get around the cab and then finally go along the skim along the top of that 18-wheeler trailer going down the semi. But we'll use those equations to solve for the drag on the trailer of an 18-wheeler, knowing that there's quite an approximation. Or we have a building sitting in the wind, and the wind is blowing along. We want to know the drag or something along the side of the building. Well, we'll use the equations, we'll make some predictions, but better put a good 25-50% uncertainty in that engineering calculation because you used equations that were developed for something like this, for something like this. For turbulent flow over a smooth flat plate, transition can occur between laminar and turbulent flow when the Reynolds number is about, and this is one of these quirky things. So we define the Reynolds number as a distance x from the leading edge. So it's rho v x over mu. What again is this x? It's not a diameter. It's the distance from the leading edge. Well, isn't that distance, isn't the Reynolds number going to increase as I go further down? Yep. That's why they chose x. Because a lot of times as you get further down, you may have the laminar region and then all of a sudden it transitions to turbulent. And so this is the critical x. And it happens at a Reynolds number when the Reynolds number is either 500, 2,000, 25,000, 500,000, or 2 million. Which one? There's no way any novice without exposure or reading ahead in the book would ever have guessed. But it's 500,000. Just like, what is the critical Reynolds number between laminar and turbulent flow for flow in a pipe? Somebody says 2,300. How did you ever get 2,300? I memorized it. No, before you memorized it, how did the engineering body of science and literature figure experimental observation? 2,300 for the Reynolds number. Well, the same thing here. It's kind of like out of a black hat. Here's a number. Where did it come from? I don't know. Experimental observation. 500,000. 500,000. And a lot of times the students will pass this class. The next semester I'll teach heat transfer. I'll ask a question. Hey, what is that critical Reynolds number for flow over a flat plate? 2,300. Well, you're off a little bit. It's 500,000. It's 500,000. It's 500,000. So, but this is one of those things where you just have to read it and accept it based on experimental observation. Define the friction coefficient. Well, what do you think that's defined as? It can be a local friction coefficient. Some viscous shear stress right at this location X. Right there is a location X. And I need to normalize that. Viscous shear stress, think about the SI units for viscous shear stress at a location. It's force per unit area. I want to normalize it. What am I going to normalize it with? Force per unit area. What type of velocity pressure? Dynamic pressure? 1/2 rho v squared. There you go. Okay. And then again, that Reynolds number, I just put it right there. That's the definition of the Reynolds number for flow over a flat plate. Well, I need to go ahead and stop. Let me go ahead and stop. We'll pick up there next time.